This video focuses on the hypothesis t-test for two dependent samples. The t-test for two dependent samples is based upon the t-test for a single sample. So just as a review, to conduct a hypothesis t-test for population mean for a single sample, which is where the standard deviation is unknown, the following conditions must be met. You must have a random sample of size n drawn from a population. The sample size must be greater than 30, or the population is known to be normally distributed. Remember, we can check that by examining the histogram of sample results. And the standard deviation of the population is unknown. If those conditions are met, then the distribution of sample means has a mean equal to the population mean, has a standard error or standard deviation of S, which is a sample standard deviation, the standard deviation of the sample, over the square root of n, and follows a t-distribution with n minus 1 degrees of freedom. Remember that a t-distribution is almost normal. Not quite, but almost. Assuming we have some hypotheses here, and the hypotheses would be that the mean equals some value versus the alternatives, that it's greater than or less than or not equal to some value. If the validity conditions are met, then the mean of the sampling distribution is V, and the standard deviation is S over the square root of n. Using these results, we can find the t-score, the calculated t-value of this observed sample mean. So again, we believe under a null hypothesis that the mean is V. We collect a sample and obtain a sample mean of x bar. Say what's the t-value? It's sort of like a z-value and standard deviation value of this x bar. X bar minus what we think the mean is, which is V, over the standard error. That's our calculated t-statistic. We can then use the t-distribution applet or the stats package like StatCrunch to determine the probability of obtaining the observed t-score, or something even more extreme. Okay, I'm going to take a look at a particular example. To do that, we have to sort of, again, remember that what dependent samples are. By definition, dependent samples are samples where the selection of an object from one population results in the selection of an object from the other population, forming matched pairs of objects. One of the key questions to ask is, if you have dependent samples, for each matched pair, what's being compared? So here's the problem. Two methods of memorizing difficult test material are examined. 9 pairs of students are matched according to IQ, okay, and assigned to one of the two methods at random. The reason they're matched in this way is we might have the belief that memory ability, testability, is dependent upon the student's innate intelligence. More intelligent students might remember more, and so they should be compared to the memory of similar types of students. Students with a lower IQ might be comparable to those with lower IQs. In other words, there might be some patterns of memorizing that are inherent in the way, in sort of the natural intelligence of students. Okay. After utilizing the assigned method, a test is given to all students, and the following results are obtained, and these are in the table. These samples are dependent because for each pair of students, the test score of the method A student is compared with the test score of the method B student. Okay, I put these data in a table, method A and method B, and the question we want to answer is there a difference in the test performance of all method A students as compared to all method B students? The first step in this process is to determine the difference in the method A and method B students. This is the key point for dependent samples, and the relationship between a dependent samples t-test and a one-sample test. We have method A scores, method B scores, but what we're going to examine is the difference in scores. If there is a difference, then we expect to obtain values that are significantly different than 0. If there's no difference in method A and method B, then most of these differences should be relatively close to 0. So, the first step, if you want to do one of these tests by hand, and we'll show you how to do it with StatCrunch in a minute, is calculate a column of the differences in method A and method B. It doesn't matter which one you choose to, if it's method A minus method B or B minus A. You just have to calculate the difference in the scores for the two columns. We'll let mu of D represent the mean of the differences for all possible pairs of students. The question we want to answer is there a difference in the mean test scores? The null hypothesis, therefore, would be that there's no difference. Versus, and since the question asks, is there a difference? Versus there is a difference. So the alternative would be it's a two-sided test. We didn't ask whether mean A is, or method A is improved over method B, or B is better. We just said, is there a difference? That's why we have a two-sided test. The decision rule is the same. We reject H0 if the p-value is less than 0.05. The t-statistic is drawn directly from the one sample. We take the sample of differences, which is in this column. So the t-statistic is the sample mean of the mean of the sample differences, rather, minus what we believe the mean of the differences to be, which is 0 under the null hypothesis, over the standard deviation of these differences, this one sample of differences, over the square root of the number of differences. In this formula I use D just to remind myself of the fact that I'm looking at the differences in the test scores. For our example, N of D, the number of differences is 9. The standard deviation of differences for all pairs of students is unknown. That's why we use a t-test. And the mean of the sample of differences, so the mean of these values, is 1.33. Okay, to conduct this test, or at least to calculate this value, and I want to show you how you get it by hand, I need to have the standard deviation of these differences. To do so, I'll go to StatCrunch. In StatCrunch, I have the differences, the method A and method B here, and here are the differences between those, A minus B. We go to Stat, Summary Statistics, under Columns. We'll look at the statistics on those differences, and compute. We get, again, the number of differences is 9, the mean of the differences is 1.33, the standard deviation of the differences is about 2.69. Okay. Oh, excuse me. So here they are. I'm jumping all around. I've added that data here, putting it into our, essentially the test statistic. We have the sample mean of the differences minus what we think that the differences are under the null hypothesis over the standard deviation divided by the square root of the sample size gives us a calculated t-value of 1.485. In other words, this sample mean is about 1.485 standard deviations larger than 0. Okay, now we could continue and go to the t-applet. What I'm going to do next is go back to StatCrunch and actually conduct this test using StatCrunch. Under Stat, under t-statistics, we have a paired option, and the paired is for dependent samples. StatCrunch will always calculate sample 1 minus sample 2. Our differences were A minus B, so we'll let sample 1 be method A, sample sample 2 rather be method B. We want to perform a hypothesis test where the mean of the differences is 0 versus the alternative where the mean of the differences is not 0. Compute, and that gives us the p-value. Okay, let's take a look at that p-value. Okay, the p-value set would say, essentially, if there's no difference in test scores, the chance of finding a difference of about 1.33 or more, or negative 1.33 or less, so something extreme, is about 17.5%. Since this p-value is greater than 0.05, we do not reject H0. Thus, there's no evidence that the mean of the differences in the test scores, method A minus method B, differs from 0. In other words, there's no evidence that one method yields better results on average than the other. Okay. Now, I want to play a little game of what if here, because this is an example where you did not see a difference. Let's take a look at what if we did see a difference. Now, to do that, what I've done, if you go back to StatCrunch, I've got, notice I have some additional testing that I've done. So I've just basically performed this test on some additional students for method A and method B and determine their differences as well. Okay, so the questions are the same. Is there a difference in the test scores between method A and method B students? For these additional students, we'll calculate the t-statistic, paired t-test, and again we will look at the differences A minus B. So sample 1 will be, and for this additional data I have it down below. Method A is the second method A down below, the second method B down below. It's still a hypothesis test where the mean of the differences is 0. In other words, there's no difference, versus the mean of the differences is not 0, saying there is a difference. And compute. And we obtain, for these, there were 16 students in this sample, and we obtain a p-value of 0.0062. In other words, with the additional students, notice that for these additional students, there were some significant differences between A minus B. It looks to me like method A seemed to be better than method B for these additional students. Putting those into the whole data set resulted in some changes in our results. Okay, so here is, for the 16 students, here were the results. We had a p-value of 0.0062. Since that p-value is less than 0.05, we reject H0. Thus, there is evidence that the mean of the difference in test scores, A minus B, for all students differs from 0. Okay, so in other words, we do reject H0, means we accept HA. But we can say a little bit more than that. The sample of differences for these 16 students for method A minus method B was 2.5. The key is not so much the value, but the fact that it's positive. Method A minus method B, when you subtract those scores, you get a positive result, which implies that if method A minus method B is positive, that method A test scores are greater than method B test scores. So, since the difference in the sample means 2.5 is greater than 0, we conclude that the mean of the differences for all students is greater than 0. In other words, there is evidence that method A results in higher test scores on average than method B. In general, when you reject a two-sided test, you would take a look at the sample mean. The two-sided test says there's a difference. When you examine the sample mean, it will say whether the difference is that these differences are greater than 0 or these differences are less than 0. Okay, lastly, I want to look at the validity. And for the validity, what I need to do is I need to examine the differences. Okay, so I want to, because for validity we want to have a random sample of 16 pairs of students. Let's assume that these students were randomly selected. For validity, the number of pairs that were selected, the number of data pairs was 16, which is less than 30. But if I go back to my results and construct a histogram, not on method A or method B, but remember, we are really conducting this test on the differences. So I calculated my differences, construct a histogram of the differences for the second test, and compute. And it looks like this. The pink is just this one pink highlighted column. I don't know why it's pink, to tell you the truth. Okay, going back to these results, this histogram is not perfectly normal, but it's a relatively small sample. In other words, there's only 16 values. There's this sort of overall symmetric shape. So this is, I would consider this to be symmetric enough. So the histogram of differences in the sample is approximately normal. And what that suggests is that the difference in test scores for all pairs of students, not just those in the sample, but for all possible pairings of these students, is normally distributed. Lastly, for validity, the standard deviation of the difference in test scores for all pairs of students is unknown. Assuming we have random selection, the histogram is approximately normal, standard deviation of the population is unknown, this test would be valid.